Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This one goes down the AAS Journal Author Series, and I'm super happy to have Marc Schaeuble with us today. Hi, Marc.
Hey, Tim. How's it going?
I'm doing really well. It's going to be another toaster in Phoenix today, so we'll probably hit 110 or so, and the humidity is up because we're in sort of Phoenix's monsoon season, so we get sort of the Gulf weather coming up into the Southwest. So, but you are a little east of me, I believe. Where are you at?
That's right. Yeah, I'm in Albuquerque, New Mexico.
Uh-huh.
So we're also seeing the monsoon starting up, but it's not quite as hot. I think we're only reaching like the mid 80s today, which is really nice.
Nice. Well, Albuquerque is, a few thousand feet
Right.
so that helps quite a bit. So
Yeah.
So that's cool. So let me just ask, is Sandia open?
Yeah, so Sandia's open. We're deemed an essential business due to the work that we do. I don't go into the office all that much currently. We're only supposed to go in, when we have classified things to work on. So I do spend most of my time working from home at this point.
Okay, cool. How long have you been at Sandia now?
Well, I started initially as a graduate student. I moved out here in 2015 and did my graduate research until December of 2018, and then I graduated and moved into a staff position. So I've been here for about 4 or 5 years at this point.
Cool, very good. What do you like to do for research, Marc?
Well, during my graduate school research, I started off doing high resolution spectroscopy of metal poor stars in the galaxy. That was for my master's. And then I moved on to lab astrophysics for my PhD project. And now I'm sort of shifting away from that into X-ray research conducted at Sandia. So.
And I think we'll probably hear a little bit about that Z machine a little bit. And
yeah, absolutely.
Cover.
Yeah.
So why don't we go ahead and get to this lovely article? And so this one is Lab Astro Definite. So we have H beta and H gamma absorption line profile inconsistencies in laboratory experiments performed at white dwarf photosphere conditions. And Marc, take us away.
Sure. Yeah. So this is research that I conducted primarily during my PhD and then finished up after I graduated. And it deals with white dwarfs, as mentioned in the title. And what we are basically doing is we're recreating white dwarf atmospheres in the lab at Sandia to try to verify the line profile calculations that are currently used in determining masses and temperatures for primarily hydrogen or Da white dwarfs. And we performed those experiments at Sandia National Labs, and I'll go into how all that works in just a little bit. And what we found essentially is that if you take the current line profile theories that are used in the white dwarf community to derive masses for these stars, what you find is that different lines give you different answers. Okay. And that's, of course, not a desirable quality you want to have in your spectral fits.
Absolutely.
So that's what the paper is about. And specifically, and this is more detail we can go over later, is that the white dwarf community currently uses line profile theories that are verified or validated using emission experiments of hydrogen. But what we do at Sandia is we have a setup that allows us to collect absorption spectra, which is actually what white dwarf stars look like. So if you go to a telescope and look at a white dwarf star, you get an absorption spectrum. Yep. But it's a more apples to apples comparison between lab experiments and actual astrophysical observations, which is why we're doing this. So if you want, I can go ahead and talk a little bit about the introduction. Sure. So as I just mentioned, hydrogen line shapes have been important for white dwarf astronomy since 1992. That's when the first paper was published on the so-called spectroscopic method. And the spectroscopic method, as the name already implies, means that you fit an atmosphere calculation of the white dwarf to an observed spectrum.
Yep.
And then that tells you something about the temperature and the density in the atmosphere of the white dwarf, because line widths and line depths are sensitive to temperatures and densities. And then you can back out a mass, and that's important for determining the age of the white dwarf, which is in turn important for constraining the age of the galaxy and the universe, for example, or also for deriving initial final mass relations.
Or these days with Kepler and TESS up, they're important for constraining the seismic signatures, I would imagine.
Right, exactly.
Cool.
And a very, as you can imagine, a very important part of these kinds of calculations, or of the spectroscopic method, is the hydrogen line shapes that basically tell you the relationship between plasma conditions and the line shape that you expect to see out of hydrogen at certain plasma conditions. And that was first proposed, so doing that kind of fitting and extracting the stellar parameters that way was first proposed in 1992. And back then they used a theory that was developed in the 70s to model the hydrogen line shapes that come out of white dwarfs. And that was great until somebody started to look at what happens if you fit the individual Balmer series lines of hydrogen, which are usually the ones that are fit in these types of astronomical fits. And they found that if you do that, H beta gives you a higher mass than H gamma, which gives you a higher mass than H delta, and so forth.
Lovely.
Yeah, and that's of course, not really what you want, because all these lines are coming from the same atmosphere, so they're all coming from the same plasma conditions.
Right.
So yeah, so that was then, and they came up with an ad hoc solution and said, okay, if we just change a certain parameter in the line profile calculation, this kind of trend doesn't happen anymore.
Okay.
But as with any ad hoc solution to a physics problem, it's completely unphysical. So it worked, which is why they did it, but that doesn't necessarily mean that you get the right answer. So in 2009, they sat down and recalculated all hydrogen line profiles specifically for white dwarfs and said, okay, now we don't have this ad hoc solution in there anymore in our line profile code. And if we fit beta, gamma, and delta with the experiment and compare that to experiment, we get the same answer every time. So this is the right line profiles to use.
Okay.
But then people went out and applied those to actual white dwarfs and found, well, the trend is still there. It's not as pronounced as it was before if you use the theory from the 70s, but there's still a clear mass trend happening between beta, gamma, and delta, and so forth. And all of this becomes even more concerning if you then, so let's just ignore that problem for now and say, okay, we're going to fit all the lines simultaneously and we get one mass.
Right.
And then that's the mass for the star. And we're not going to worry about the mass trends for now. If we then take those masses and compare them to another method, which doesn't rely on line profiles at all, it's called the gravitational redshift method, which basically relies on the fact, your white dwarf is very small and dense, so it has a huge gravitational field. When a photon leaves the surface, it's going to get redshifted, and based on that redshift, you can extract a mass of the object. So it's physically speaking a little bit more straightforward than the spectroscopic method, because you're not relying on atomic physics to tell you what the mass of the star is. You're really just relying on general relativity to tell you what the mass of the star is, which is a better understood and physically more straightforward in principle anyway theory. So if you compare those two masses, what you find is that the gravitational redshift mass is higher than the spectroscopic mass. Okay. So that's of course another issue, which points to the fact that either the gravitational redshift or the spectroscopic mass is not, one of them is not right.
So when you say the gravitational mass is higher, are we talking 1%, 10%, 50%?
Yeah, it's roughly about 10%. Okay. That's how much higher it is. And then you can throw a third mass determination method into the mix. So for certain white, yeah, for certain white dwarfs, which are in binary system, you can also obtain a dynamical mass. And then you find that mass doesn't agree with either the gravitational redshift or the spectroscopic mass. So there's a whole, I would say that the ability for us to measure masses of white dwarfs correctly is at best questionable at this point if you take all those considerations into account.
Traditionally, binaries have been the gold standard.
Right. Yeah. And there's a particular binary, Sirius B, which is the gold standard in white dwarf astronomy. But there have also been questions about whether that mass is actually accurate, because it's really difficult to measure because it's right next to a huge bright object, right? So
Fair enough. Okay.
it's a bit complicated. And there's people out there like Martin Barstow who've dedicated years and decades to trying to measure the mass of Sirius B correctly using the dynamical method. And if you want to know more about that, go talk to him, but he'll tell you all about the shortcomings of dynamical masses as well.
Okay. I do.
Now, the gravitational redshift method and the dynamic mass methods can only be applied to very select few white dwarfs. So by far not the majority of the ones that we know about. For dynamical mass, you have to be in a binary system. And then for the gravitational redshift, there's other, like you have to cancel out the proper motion of the star so that you isolate really only the shift caused by the mass of the white dwarf. So there's other complications there. So the spectroscopic method, while it has its shortcomings, is really, really, really powerful because you can apply it to virtually any white dwarf that you can collect a spectrum of, which is the vast majority of white dwarfs. So we decided to attack the problem with the disagreeing masses from the disagreeing lines, from the different lines in the spectroscopic method using experiments. And that's what section 2 describes is our experimental platform. So this project was started back in 2011 by another graduate student from UT Austin called Ross Falcon. So he developed the platform at Sandia National Labs, and he published a paper on H-beta line profiles collected in the experiment that we collected as part of his PhD thesis.
Okay.
And basically, the way that the platform, well, no, let me step back and first talk to you about how the Z machine works. So we do all these experiments at Sandia National Labs at the Z machine, which is a pulsed power accelerator. That's what it's called. And the way that the Z machine basically works, it's about the size of half of a football field, and the building is about 3 stories high. So it's really big. And what it does, it converts power that's stored in capacitors into an X-ray source by compressing the power in time and in space. So you take all this massive power, you compress it down, and then you get an X-ray source essentially out of it. And that X-ray source is used for a whole bunch of different things, amongst one of which is our experiment. And in figure 1, you're looking at the platform that we use to create the spectra that we collect that are shown in figure 3. And the platform works, it's quite simple actually. So I outline I show the Z pinch there, which is the X-ray pinch that's created by the Z machine. So it creates all these X-rays, and then these X-rays travel to the gas cell, which is what you're seeing here. And this gas cell is filled, which in our case, with hydrogen, because we want to look at hydrogen line profiles. So the X-rays, they travel through the hydrogen because they're so high energy that they don't interact with the hydrogen directly. They travel to the gold back wall that's pointed out there, and they heat up the gold back wall to about 4 to 5 EV, which is 45,000 to 55,000 Kelvin roughly. And then over the course of 200 nanoseconds, it deposits all that energy back into the hydrogen gas and turns the hydrogen gas into a plasma. And the plasma reaches about 1 to 1.5 EV, so 11,000 to 16,000 Kelvin roughly. So right at the conditions that we would find in your garden variety hydrogen white dwarf.
Okay.
So we're right at parameter. And even the electron densities that result out of this are at about 1 times 10 to the 17 per cubic centimeter. So again, right at the density that we find in your average hydrogen white dwarf. And then we look at the plasma using 3 different lines of sight. One of them is the absorption line of sight, which looks at a gold backlighter there, which is also heated to about 4 to 5 eV. So you're looking through a 1 eV plasma at a 4 eV background, so you're going to get an absorption spectrum. Then we have emission and absorption, and continuum. And the emission is just, you're looking at the self-emission of the plasma, you're not looking at any background. So that's the blue spectrum you see over in figure 3. The absorption is the red spectrum. And then we also have the continuum line of sight, which just looks at the continuum of the backlighter itself. That's used for calibration purposes. Oh, and it's shown more in figure 2. I didn't even realize that. So everything I just described is basically also demonstrated in figure 2.
Yep, all good.
Yeah, so when we do all that, we get the spectra we see in figure 3. And we collect data, as I mentioned earlier, for about 200 seconds, just 200 nanoseconds, my apologies. So one of the things that we did first is we have these spectra and we can calibrate them in several different ways. I don't think I talk about that in the paper. I'm not going to bore the audience with that, but basically we can convert them into a transmission spectrum, which is what you get out of a white dwarf. And in section 3, I describe how we then take those transmission spectra and convert them into electron density. And it's really simple. We do the same thing that white dwarf astronomers do. We take the line profiles and we fit line profile calculations to the lines. So that's not exactly how the white dwarf community operates. What they do is they have a white dwarf atmosphere calculation, and then they put the hydrogen line profiles through the atmosphere calculation, and then they have a resulting spectrum. We don't do that because we don't look at an atmosphere. We look at a single slab of temperature and density, so we can fit the line profiles directly.
Right.
And the results are shown in the top panel of figure 4. So we fit H beta and we fit H gamma. And we do that using several different theories, particularly 4 theories that we use to fit these spectra. One of them is called VCS, Vidal-Cooper-Smith. That's the one that was done in the 70s. That was the one that the white dwarf community used previously. Then there's Tremblay and Bergeron, which is the white dwarf update from 2009. And then there's Higoso's, which is another theory from also the early 2000s, I think. And then there's Xenomorph, which is a theory that was developed by another graduate student who also works at Sandia, who's also a UT graduate student who also worked on this. So we used these 4 theories to try to see, do we get differences between beta and gamma, and can we somehow recreate what we see in the white dwarfs? And as I show in the top panel of figure 4, that's exactly what's happening. So if you fit beta and gamma independently, what you find is that the electron density inferred by beta is higher than the electron density inferred by gamma.
Okay.
I remind you that in the white dwarf, you see the exact same thing. If you fit beta, you get a higher mass or a higher electron density in the atmosphere than you do for gamma. Okay. So this is both encouraging and discouraging, because it's encouraging because we're seeing similar trends in the lab, and it's discouraging because we're not supposed to see that. Because if you perform these fits in emission, you find that beta and gamma give you the same answer. So this appears, this appears to be a problem only applicable to the absorption, which is weird because if you look at any stellar atmosphere textbooks, they will tell you emission absorption is the same thing. It's complete redistribution. You're not going to have any differences between the two, right? So that's of course concerning. We repeated these types of tests for 3 different experiments that we collected over the course of about 2 years, and those results are shown in figure 5. So what we find is that across 3 different experiments that were collected at very different electron density ranges, the difference between beta and gamma and electron density is always right about 35%. And beta always gives you an electron density that's about 35% higher than that of gamma. And again, that's not good, but it's also something we see in the white dwarf community. So perhaps there's something to it.
Right.
You could go out on a limb here and say, well, this clearly proves that emission and absorption aren't equal and there's something else. But of course, that's a huge and strong statement to make, right? Especially since we're experimenters. What we decided to do then is to look at, okay, we're doing experiments. Every experiment that's ever been conducted in the world has gradients associated with it, right? Our experiment has plasma gradients. Everybody else who does experiments has to deal with gradients. So, and this behavior could potentially be caused by experiments in the platform. So we went to great lengths to make sure that we understand what the gradients are in the platform and what kind of effects they have on these electron densities that we're extracting from beta and gamma.
Good.
That's basically what the rest of the paper is about. So that's section 5, potential sources of the beta gamma disagreement. And there's 3 different things that we looked at. One of the first ones is the self-emission correction uncertainty.
Yes.
Right, so I'm going to explain what that means. So if you look at a star, you look at a really bright backlighter, so if you look at then the equation of radiative transfer, you can easily take the self-emission part out of it because the backlighter is so strong, so bright, right? It's not going to really affect your observed line profile. That is not the case for the experiment. We don't have that bright of a backlighter where we can just say, okay, we're going to ignore that and not even attempt to correct for it.
Okay.
So, right, so the way we do that is that you have to put the experimental spectra on an absolute scale. And any experimentalist will tell you that and even for stellar spectra, it's really difficult to put them on an absolute scale, on an absolute flux scale. But you have to do that if you want to perform the self-emission correction properly. Because if you over or under account for the self-emission, your extracted line profile will be incorrect, right?
Yep.
So we do that by doing a whole bunch of different calibration tests, and then we can say, okay, with a 20% certainty, this is what the extracted line profile should look like. But we don't really know whether the calibrations that we're doing on the data are as accurate as we think they are. So we did an extreme test in this paper. What we basically did is you can make a physics argument for the fact that if you have an emission profile and an absorption profile and they're of the same source, your emission profile can never be stronger than your absorption profile, right? If you look at the equation of radiative transfer, it doesn't allow for that, because if that was the case, then you would get negative transmission, which you can't have. Right. That's physically not possible. So what we did is we completely ignored the calibrations for the emission data and just scaled it directly to the dip of the absorption so that we get the maximum self-emission correction out of our experimental data. Redid the fits and found it doesn't really matter all that much because our emission is not that strong, especially early on in the experiment when the backlighter is really hot, right? Because the hotter your backlighter, the less effect you're going to have of the self-emission on your absorption profile.
Yes.
Right. So that's the first test that we did, and that's basically what's described in section 5.1 and also shown in figure 6. So I show these different scaling factors here, and the scaling factor that we derive using our usual calibration method is the 1.4, and then we scale it up to 1.7, which means that the emission is directly touching the absorption, so that's maximum self-emission correction. And then we also do a lower limit of 1.1, which is the orange line, which gives you, what if we're overestimating for self-emission, because that would also change your line profile that you extract from this type of data. So if you go down just a little bit, keep going to the next figure, I think.
Figure 7?
Right, so figure 7 just gives you the comparison between the different So what the emission versus the absorption intensity is, and as you can see, as a function of experiment time, it's quite low, even in the plus and minus 20% case where we scaled it directly to the absorption depth. And what we found is that it doesn't really matter all that much. I don't remember exactly what the precise number is, but it's something on the order of 6 or 7% that your electron density changes as a function of how much self-emission you subtract. So that was a big one because the calibration is one of the most difficult parts to do of the entire experiment. So figuring out that that wasn't the case was great. And then another thing that we looked into, as I mentioned earlier, is the potential sources of gradients within the platform. And we used a combination of simulations and experimental data to help us sort of put bounds on the upper and lower limit of the gradients. And if you go back to the figure,
just to
sure.
Just for my own edification, most of those gradients are coming from the fact that the experiment has walls, or is it non-uniformity within the plasma itself?
So we think, yeah. So the walls play into it. It's also the way that the gas cell is actually irradiated by the Z-pinch, and there's also view factor effects, and that's one of the things I'm about to go into. But there's several different effects that play here. And I think that's most easily explained if we go back to the figure where I show the platform, which I think is figure 2, if I remember correctly. Oh, it's figure 1 actually. Yeah. So when the experiment is happening, this whole thing that you see here is filled with hydrogen gas. So there's even hydrogen gas in the buffers there, which are designed to protect the data collection optics from the plasma that's in the central portion of the gas cell, so that they don't, like your lenses and your fiber doesn't melt as you stick it into a 10,000 degree. Yeah, you don't want that to happen. But of course, there's then the possibility that some radiation makes it into the buffer, that the buffer heats up as well, and that you then have extra emission or absorption that if you look at the emission line of sight, which goes through 2 buffers, as opposed to the absorption line of sight, which only goes through 1, could affect both of those data sets individually and differently. So we had to account for that. Another thing that we accounted for was the fact that the Goldbach wall, and this is where the view factor effects that I just talked about come into play. The Goldbach wall is 120 millimeters long. Other simulations and other experimental measurements at Z show us that the radiation, because we're very far away from the source, we're about 35 centimeters away from the actual Z-pinch. The radiation at that point is fairly uniform. So the Goldbach wall should get irradiated uniformly by the Z-pinch. But of course, if you then imagine your plasma particle at the center of the Goldbach wall, you are going to receive radiation from all parts of the Goldbach wall, right?
Right.
And if you then take the view factor effects into account, the portion directly behind you in the Goldbach wall is going to heat you more than the very edge of the plasma. If you're at the center of the Goldbach wall, you receive radiation from all parts of the Goldbach wall, but of course the edges are less than the center. If you shift your view to the edge, that's going to be slightly different. You're still going to get radiation directly from the Goldbach wall, but all the contribution from the other parts of the Goldbach wall is going to be less. So we expect the plasma to be cooler at the edges than at the center, just due to that view factor effect, right?
Yes.
And one way we can check for that is using the continuum line of sight, because if you look at the continuum line of sight, which is the green line, it looks down onto the backlighter, which is at the very edge of the gas cell. So if we can extract electron densities and temperatures from the continuum line of sight, we can then say, okay, we can compare the absorption line of sight, which gives you the integrated temperature and density along the Goldbach wall, and we can compare that to the electron density that we find from the edge and see, is there a difference? And if there is, that points to a gradient that we have to account for.
Right. Okay.
If we go back, if we go back to section 5, the one we just left, that's what that section is about. So I talk about the buffers, where we basically find, okay, the buffers don't really matter all that much. I ran a whole bunch of simulations that put a 1.5 eV plasma right next to a slab of gas, how much would that heat it? It's not that much. And on top of that, we have apertures that help constrict the radiation flow from the main body of plasma to the absorption buffer. So that shouldn't really be that big of an influence on our actual measurements. And then the gold back wall and the backlighting surface. So I just described the gold back wall, what the issues are there. And then the backlighting surface itself, you know, if you think about the absorption line of sight and you're looking at the absorption at the gold back wall, the backlighting surface, obviously the closer you get to the surface, the hotter it's going to be because you're looking directly at it. So there's a slight increase in temperature and density towards the very end of the absorption line of sight that could also, that's not present in the emission, that could also throw off the uniformity in our plasma.
Right. Okay.
So taking all of that into account and also the absorption and the emission line of, sorry, the absorption and continuum line of sight and looking at figure 8, you can constrain the plasma, right? You can, the figure 8 basically shows how you can use the absorption and continuum data to derive differences between the bulk plasma parameters and the ones right at the very edge. And I show different spectral lines for H beta in figure 8. So the red is from the absorption line of sight and the green is from the continuum line of sight. And if you compare just the measured full width, yeah, it's good to zoom in on that. So it shows 0 and 60 nanoseconds, and the red is the continuum and the green is the, the red is the absorption and the green is the continuum. What you find is, and then the dashed lines here are the full width half areas of those lines. If you compare between 0, where the continuum appears to be slightly broader than the absorption, and then the 60 nanosecond data where the continuum is definitely narrower than the absorption data, that already indicates that there is a true plasma difference between the continuum and the absorption line of sight. And you can do that for every single time step that we have in the experiment. And then based off of that, you can derive what the difference between the bulk plasma parameters and the edge plasma is. And that gives you an idea of what the temperature gradient and the density gradient within the platform must be. Like a very rough.
Okay.
Does that make sense? Sort of?
Yeah. Kind of sort of off topic, but let me ask 2 questions. So,
sure.
So what is the total time from when you start measuring to when the plasma cools off enough you're outside the range? So what is our time scale here? Total?
So in this paper, yes. Well, it depends on what time you talk about. So could you cools off enough for us to measure, or what do you?
When do you start? So what is the time between when you start measuring and when you stop measuring?
Oh, I see. So it's about 100 nanoseconds. That's the data that we feel most comfortable with.
Okay, and within that 100 nanoseconds, what's your time resolution?
So sorry, I should have mentioned that earlier. I apologize.
That's okay.
We collect our data on street cameras. So that's time resolved and spectrally resolved cameras. They perform a streak. And the time resolution of those is about 1 nanoseconds, but we integrate in 10 nanosecond steps to increase the signal to noise. Because if you use the 1 nanosecond, a single pixel row, that's
noisy.
Yeah, very, very noisy. So what you're looking at here is all 10 nanosecond integrations.
Got it. Thank you.
Of our data.
I'm with you.
Yeah. Okay. So if we have all of this, you can zoom back out, and then you can basically, take the backlighter into account. And if we go to the next plot where I think, oh, right. So if we have the continuum and the absorption data, what we can do on figure 10, right, we can determine what is the ratio between the continuum line of sight electron density and the absorption line of sight electron density as a function of experiment time, right? And I show here, we consider.
Okay.
Yeah.
Right on cue with that question. Go ahead. Okay.
For about 100 nanoseconds. But for this paper, just to stay safe, we cut our analysis off at 60 nanoseconds because that's where we trust the calibrations the most. So we think they're fine beyond 60, but we're most confident from 0 to 60, basically. And what we see is that the ratio of those two electron densities, continuum to absorption, is continuously going down. What that means is that the absorption line of sight, the integrated plasma parameters, are getting hotter or more dense as compared to the continuum line of sight, which is at the edge of the plasma, due to whatever effects, right? This is happening. This is what the data is telling us.
Right.
So the gradient gets worse as time goes on, but it also appears to flatten, or it also appears to reach steady state once you reach about 60 nanoseconds, because the ratio doesn't change anymore. The ratio between the electron densities doesn't change.
Right.
And since you're dealing with a hydrogen plasma, there's a very close correlation between electron density and plasma temperature, because your hydrogen only has one electron. So if you have more electrons, you're going to have a higher temperature, right? So that's one of the beautiful things about working with hydrogen. Is it's very the stuff like that is very easy to understand. You know, that's not necessarily the case for other atomic species, but
sure, like iron.
Exactly, like iron. That's much more difficult there. But so the point of this plot, or what this plot showed us, is really there is a difference between the bulk plasma parameters and the edge, and we need to take that into account when we do our analysis. And what you can do is you can take this electron density ratio and turn it into a temperature ratio. Again, very easy for hydrogen because you're only dealing with a single electron system. And that then lets you derive what the peak temperature must be in the bulk plasma parameters and what the temperature at the edge of the plasma must be, because the continuum line of sight is telling you that. And so if you take the most extreme ratio, which is at about 0.2 here of the two, you can then derive your most extreme gradient that you potentially have in the platform. Right. And that's what we did. And I think that's in the next plot, if I remember correctly. So section 7 talks about how to do all that. And then here are the two gradients in figure 11 and 12. One of them is in temperature and one of them is in electron density. And the figure 11 is temperature, figure 12 is electron density. And these are the gradients along the different lines of sight. So we have emission and we have absorption. And excuse me, for this, I only show emission. I don't really show absorption. Excuse me, I show absorption, not emission, because we looked at the absorption data. I did a similar exercise for emission, and it's very similar, except the influence of the backlighter that I point out in both the electron temperature and electron density plot.
Okay.
We derive two different versions of this gradient. One of them is a very extreme gradient, which I show in red here. And that's basically just derived from, okay, if you take the continuum to absorption electron density and just say, okay, there's one hot spot in the very center of our gas cell, and then the temperature and the density basically make a very kind of like a house-shaped temperature decline, a linear temperature decline towards the edges of the gas cell. That's what you would get. Now, if you think about this from a physics perspective, even if such a temperature gradient existed at the very beginning of our experiment, it wouldn't last for very long because things would equilibrate very, very quickly.
Okay.
So you wouldn't have those very sharp turns for a long time and these very steep linear temperature gradients. A more realistic version of the gradient, which also conforms to the data, or the constraints imposed by the absorption continuum data, is shown in black here. So that's what we think is a more realistic gradient, because we don't really believe that there's a huge hotspot in the center of the cell.
Sure.
Intuitively, it doesn't make a whole lot of sense. But just to be on the safe side, what we then did is we took this extreme gradient and simulated what would a hydrogen line profile look like if you fed it through this extreme. So we're basically doing the same exercise that white dwarf people are doing, is they're taking a hydrogen line profile, feeding it through a temperature and density structure, and looking what comes out the other end, reanalyzing that and trying to see, okay, could this gradient potentially be responsible? Does that gradient affect beta somehow differently from gamma?
Right.
And could that potentially then mean that you get different electron densities from beta and gamma due to the gradient that you're seeing here. So that's what we did in section 7.2, and I think I show, oh, I don't show that. Okay, sorry, I thought there were many more plots in here. But basically what we find, if you do all that, yeah, so that's a different figure. But if we do all that, what we find is that if you then look at beta and gamma and compare their electron densities, even with the gradient applied to the profiles, the difference in electron density between the two is almost negligible, because it appears that the gradient affects both profiles equally, which makes sense if you think about it. But yeah,
Okay.
we wanted to cover our bases. So the point of all this being, the gradients don't seem to be responsible for the electron density difference that we're seeing.
Right.
It's not our data analysis methods either. So what we're left with is that we have this data, and we're seeing a 35% difference between beta and gamma in absorption, which we don't see in emission. A similar trend is seen in white dwarf spectra. Nobody really knows why, and there's several uncomfortable conclusions that you could draw from this if you wanted to. Although we didn't do that in the paper because we don't think we're ready to claim that yet. More work has to go into this. But as I mentioned earlier, you could claim absorption and emission are different, which would be a huge claim, which would need a lot of extra.
That's uncomfortable.
Yeah, very uncomfortable, which is why we didn't go there, and we don't think we have the evidence for that at this point.
Right.
So that's one thing. You could make a lesser claim of saying, well, really the way we're validating the line profiles in emission is somehow not compatible with absorption, right? So there's something weird going on that we're not taking into account with the validation in emission and then applying that to absorption. But one thing remains certain, I think, is that we see these trends in lab data, we see it in astrophysical data, and it really is an impedance into how well we're able to obtain masses of white dwarfs, and that has implications for a whole host of astrophysical applications, you know, ages and initial final mass relations. And all of those are important for other astrophysical areas like galactic evolution and things of that nature. So I think the main point of the paper that we were trying to get across is exactly that, is that we shouldn't claim victory just yet with the spectroscopic method, even though it's been proven to be really powerful and easy to use, and that's great, but the details need to work out in the atomic physics before the white dwarf community can really say, you know, this is the gold standard of mass determination methods for white dwarf, and you should believe these masses. So, and I think that's the main point that we were trying to get across here.
Oh, that's very cool. So since you kind of touched on the topic, let me ask, where do we go over the next couple of years, let's say half decade, on trying to understand where this 35% discrepancy comes from? Are there more experiments in the pipe, or where do we go?
Yeah, so they've hired a new postdoc who's taking these data and running with it. So he's now doing experiments that are trying to quantify, because what we did for this paper is we said, okay, we have this data at the very edge of the gas cell and then the integrated electron density and temperature. What he's doing, he's looking to quantify the gradient along the gas cell, looking down at different spots to try to see, is the gradient that we derived actually correct? So that's, of course, a huge thing that we have to do. We're also looking to incorporate independent diagnostics to make sure, because what we're doing right now is we're pointing at line profiles and saying, okay, we don't have independent plasma diagnostics that tell us the temperature and density independently. We're using line profiles to tell us something is wrong with the line profiles, but that inherently hinders you in saying what exactly the problem is, right? Because you're using that same logic to also point out the problem. So that's independent plasma diagnostics is another issue that is currently being worked on.
Cool.
And then we've also expanded into helium. So there's also issues with helium white dwarfs, and I realize I'm way over time here, and I apologize.
It's all good. It's all good.
There's also mass issues with the helium white dwarfs that are currently being investigated. That's another part of my PhD thesis, and I'm wrapping that up. I don't want to go into that in too much detail, but
that's fine. We don't have to spill that now. But the point is, it's still a mystery.
right.
It's an important mystery, and it's being worked on from
Right.
several angles. So that's very cool. That's very nice. So stay tuned, people. Lots of interesting stuff coming. Very cool. Well, Mark, I want to thank you so much for spending some time and walking us through your lovely paper.
Sure. Thank you for having me. I appreciate the opportunity.
You're welcome. And we'll see you on the next one, everyone. Bye-bye.